Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lectures, we have introduced the concept of discrete Fourier transform, we had derived the analysis and synthesis equations, and we had also seen an example for solving for finding the discrete Fourier transform for a discrete time signal. And we had also seen that the value of n should be chosen greater than or equal to L in order to obtain the proper DFT, where this L is the length of the signal. So the n-point DFT for any signal x of n can be calculated using this formula, whereas the inverse DFT can be calculated using this synthesis equation. So now in this lecture we are going to look at two important aspects for this DFT, that is periodicity of x of k and x of n and the modulo operation. So let us start with the periodicity. So for that, let us first go for the periodicity of x of k. So the analysis equation is given as x of k is equal to summation n running from 0 to n minus 1 x of n into e to the power minus j 2 pi k n by n. So now let us try finding out the value of this x of k plus n, which is equal to summation n running from 0 to n minus 1 x of n into e to the power minus j 2 pi. So it is k plus n into n divided by n, which can be written as summation n running from 0 to n minus 1 x of n into e to the power minus j 2 pi k n by n multiplied by e to the power minus j 2 pi k capital N. So it would be 2 pi capital N into small n upon n. So let us consider this exponent here. So we have it as e to the power minus j 2 pi capital N into small n upon n. So this n gets cancelled and we have e to the power minus j 2 pi into small n. Now we can observe that we have here the term as integer multiple of 2 pi, which means that this complex exponent is going to give us the value as 1. And when we substitute this in this expression here, so we have x of k plus n is equal to summation n running from 0 to n minus 1 x of n into e to the power minus j 2 pi k n upon n. And if we observe the original expression of DFT, that is x of k, and compare it with this expression, we can observe that it is exactly the same. So we can conclude that this x of k plus n is equal to x of k. What does this mean? This simply means that this x of k is periodic with a period n. So this x of k is periodic with period n. So we can have here n or 2n or 3n. In all the cases we would just have some constant being multiplied here, an integer constant being multiplied here. So we can say that this x of k will be periodic with period n, because anyways this 2 pi into n into some integer will be again an integer multiple of 2 pi, which would lead to 1, and therefore this x of k plus say L times n will always give us x of k, which means that this x of k is periodic with a period n. Now another thing that we need to keep in mind is that this periodicity leads to consideration of a unique range for x of k, which means that the unique range of x of k is from 0 to n minus 1, and after that it is going to repeat. So this is the case for the x of k. So now let us look at the periodicity for x of n. Now we have the synthesis equation, which is given as x of n is equal to 1 by n summation k running from 0 to n minus 1 x of k into e to the power j 2 pi k n by n. Therefore x of n plus capital N is given as 1 by n summation k running from 0 to n minus 1 x of k into e to the power j 2 pi k into n plus n divided by n, which is equal to 1 by n summation k running from 0 to n minus 1 x of k into e to the power j 2 pi k n by capital N multiplied by e to the power j 2 pi k capital N by capital N. So this factor gets cancelled here, and again we are having an integer multiple of 2 pi as a power of this complex exponential, and therefore this term here is again equal to 1, and therefore we have it as 1 by n summation k running from 0 to n minus 1 x of k into e to the power j 2 pi k n by capital N, which is equal to x of n. So if we compare these two expressions here, they are exactly the same. So we can write x of n is equal to x of n plus capital N, which again means that this x of n is periodic with period n. But if we consider the original signal, we know that the initial considered signal is not at all periodic with period n, but has some length L. So original signal x of n was not periodic but was finite duration signal of length L. We have found the DFT x of k, which is n point DFT, which means discretize omega axis into n parts or n equal parts And we know that this discretization leads to inherent periodicity in the time domain, and same thing is observed here. So this periodicity in the time domain is obtained due to this discretization of omega into n equal parts, which is the inherent periodicity. So what we observe here is this x of k as well as this x of n exhibits some kind of periodicity with a period n. So now let us move ahead and look at the modulo operator. But before moving ahead, let us first understand what this modulo operation is. So if we consider a mod b and consider this b to be a positive integer, then in that case this a mod b would be remainder obtained when we divide a by b. For example, if we have the value of a as 3 and b as 4, so we know that if we divide this a by b, that is 3 divided by 4, then we are going to get the remainder or the value of 3 mod 4 as 3. Similarly, if we consider a as minus 3 and b as 4, so in that case if we divide this a that is a by b, so if we try finding out the value of mod or minus 3 mod 4, then in that case we are going to get the remainder as 1. So how is it? So if we divide this minus 3 by 4, so we have here minus 1 minus 4, and so it would lead to 1. So the remainder that we are obtaining is 1. So this modulo operation is simply remainder provided the value of this b is a positive integer. So now let us see what is the significance of this factor here in our case. So for that, let us consider the signal which we had been considering since the example, that is x of n is equal to 1 2 3 4, which is used for finding out the 4-point DFT, that is the value of n is equal to 4, and we know that in that case this x of n will be having a periodicity with a period n, which means this x of n would be repeated after every 4th sample. So this is here x of n, this is x of n minus 4, and the factor here or the terms here are x of n plus 4, and this would be repeating till infinity, from minus infinity to infinity. So this is the case that we are having here. So now let us represent this periodic signal that we are obtaining after discretization of omega axis as x of n. So if we observe carefully, the value of x of 0 is equal to the value of x of 4, and it is equal to the value of x of minus 4. So we have x of 4 is equal to, so x of minus 4 is equal to x of 0 is equal to x of 4, and it is equal to 1. Similarly, we have this x of minus 3 is equal to x of 1 is equal to x of 5. So we have x of minus 3 is equal to x of 1 is equal to x of 5 is equal to 2. Similarly, we have this x of minus 2 is equal to x of 2 is equal to x of 6. So we have x of minus 2 is equal to x of 2 is equal to x of 6 is equal to 3, and similarly we have x of minus 1 is equal to x of 3 is equal to x of 7. So we have x of minus 1 is equal to x of 3 is equal to x of 7, which is equal to 4. So we have these cases here. Now we just need to observe the domain values of all these things and consider its modulo operation with respect to n. So what we need to find is mod of this domain here with respect to n, and we have the value of n as 4. So if we look at minus 4 mod 4, so it would be equal to 0. Similarly, if we look at the modulo operation for 0, that is 0 mod 4, again it would be equal to 0, and similarly if we have 4 mod 4, again it would be equal to 0. Similarly, if we consider the value of minus 3 mod 4, so we had found it as equal to 1 in the example here. So minus 3 mod 4 is equal to 1. Similarly, if we divide 1 by 4, we are going to get the remainder again as 1, and similarly if we divide 5 by 4, we are again going to get the remainder as 1. So if we have minus 2 mod 4, the remainder would be 2. 2 mod 4, the remainder would be equal to 2, and this 6 mod 4, the remainder again will be equal to 2. Minus 1 mod 4 is equal to 3. Then we have 3 mod 4 is equal to 3, and this 7 mod 4 again would be equal to 3. So what we observe here is the modulo operation of these terms, that is minus 4, 0 and 4, is exactly the same, that is minus 4 mod 4, 0 mod 4, 4 mod 4 is equal to 0, and similarly the modulo operation of minus 3, 1 and 5 with respect to 4 is again same, that is equal to 1. The modulo operation for minus 2, 2 and 6 with respect to 4 is again 2, which is same for all, and the modulo operation for minus 1, 3, 7 is again same, which is equal to 3 for all the cases. So what we can see here is, if the domain value, or if the value of n, small n modulo capital N, is same for the values or the other for different values of n, then we are going to have the same range value for the given signal. So what I mean to say here is, the value of n mod capital N is equal to the value of x of n. So in this example, the value of n mod 4 is equal to x of n. So if we consider the value of n is equal to -1, then we have the value of -1 mod 4 as 3. So this is x of 3 will be equal to x of -1. So this is very well true here. So x of -3 the value of x of 3 is equal to x of -1. Similarly, if we have the value of n as 7, then x of 7 would be equal to x of 7 mod 4, and we know that 7 mod 4 is again equal to 3. So this x of 3 is equal to x of -1. So therefore what we conclude here is x of n mod capital N is equal to x of n. And this n mod capital N can be also written as x of n mod capital N is equal to x of n. Now what does this modulo operation lead to? So if we observe in this diagram here and start from 0, 1, 2, 3 and reach till 4, now at 4 again we have the same value of x of n as we had here, that is at x of 0, which is equal to 1. So if we try shifting this signal towards right, so we are actually having some kind of circular shift. That is, if we shift this by one factor, then this 1 would be here, this 2 would be here, this. So what I mean is, if I shift this signal towards right, so I would be having this 1 here, this 2 here, this 3 here, and this 4 here. But if I shift it by a factor of 4, then I would be having this 1 here, 2 here, 3 here, 4 here. Similarly, the factor which was present initially here, that is from -4 to -1, would be now present at this location. Similarly, the factor which was present from -8 to -5 would be available here. So what do we observe is, when we shift by a factor of 4, we are again getting back the original signal. Now what does this mean? This means that instead of having a linear shift, we are getting a circular shift. So let us try to understand this. So let us represent the value of this x of n which we had, this x of n which we had as 1, 2, 3, 4, where this 1 is located at 0, represented in circular fashion like this. So this 1 is x of 0, this 2 is x of 1, this 3 is x of 2, and this 4 is x of 3. So basically this is the direction of increasing value of n. So this is the direction of increase of n. So now we have x of 0 as 1, then we shift circularly, so we have x of 1 as 2, then we move ahead, we have x of 2 as 3, Then again when we move ahead, we have this x of 3 as 4, and now if we go ahead and calculate the value of x of 4, we again have it as 1. So this x of 0, we know that it is equal to x of 4. Again when we go ahead, so here we have x of 5 which is equal to 2. So again here we have it as x of 5. Similarly, here we will be having x of 2 is equal to x of 6 which is equal to 3, and for this 4 we would be having x of 3 is equal to x of 7 which is equal to 4. So basically when we are shifting again by 4, so we are again getting back this original signal, that is x of 0, x of 1, x of 2 and x of 3, which means that the representation that we are having here simply represents x of 0 mod 4. This 2 simply represents x of 1 mod 4. Similarly, this 3 represents x of 2 mod 4, and this 4 represents x of 3 mod 4. So we can represent this signal x of n when we discretize or when we find the 4-point DFT or n-point DFT in a circular fashion, something like this. So in this lecture we had seen two important aspects, that is the periodicity of x of n and x of k. We saw that this x of k and x of n both are periodic with a period of capital N. And we have also seen the modulo operation for x of n, that is we have this x of n is equal to x of n mod capital N. So let's stop here. Thank you.